Hello everyone. We're starting this journal club. This is the fifth journal club about quantum machine learning in the using a quantum classifier for medical data. Or well, this presentation is about from Mexico. The people is Luis Emilio, Abel, Saúl Puente, and Jesús Salvador. They are from Mexico and they will speak this presentation. You can start.
Okay, thanks. Good morning, everyone. Good afternoon. Okay, we're going to talk about quantum classifier for medical data. This project was made for a hackathon, an IBM hackathon in the SIG, and also a part of the Congress in our institute. Um, okay, so this model or this learning model is based on quantum variational circuits. The quantum variational circuits is a part of quantum variational algorithms. This quantum variational algorithms is based on quantum computing based on gates. This quantum paradigm is thought that it can be computing universality. So why this thing happens is because it's an hybrid algorithm. We use the power of classic computing and quantum computing to achieve a quantum leverage. The limitation in our NIST device today is the limited number of qubits, as everyone knows, and the limited number of secrets we can encode in these gates. Mm, yeah, so a solution was proposed is to distribute this computational in quantum as a quantum part and a classic part, where in the quantum part we encode our variational gates. These variational gates are trainable. We encode a cost function in our circuits. That's the blue boxes that are variational, and these parameters are tuned classically with classical optimization algorithms we are that are um, explored, like Adam in neural networks or Covilla indeed writing the same methods. Yeah, so it's proven a good method to achieve better results. Yeah, the general scheme of work in these variational quantum algorithms is first to encode the data, define an ansatz, where an ansatz is just the variational part of the gates, the variational parts of the algorithm, and then we train these parameters of the ansatz. We just define a training model. We refer to the training algorithm or a training technique. If we want to train just a certain number of labels or make another novel technique in these circuits, just to avoid the trainability issues like varying plateaus, vanishing gradients. Yeah, and then we measure the result and cycle in this algorithm. Okay, so we are just to jump in the first part, in code part.
In the process of data analysis, the first step is the normalization of the data. This consists in the preparation of the same for a later analysis. The normalization of the data varies according to the type of data and the objective of the analysis. In this case, quantum algorithms will be used, so the normalization process will focus on the preparing the data for this type of analysis. And this normalization process will start by shuffling the data to introduce some randomness, remove irrelevant attributes, and normalize the data using a scalar preprocessing mean scalar in the range of -2p to 2p, 2pi. This to make sure that we use the Hilbert space properly as we encode the data into the quantum states through angles of rotation. We divided the data into a training set to create the model and a test set to test the model, keeping the size of the test set at 45% of the total data set.
Okay, let's go to talk about how to encode the classic data in quantum state or in quantum data. So first, we have a quantum embedding process that is that map the classic data in a Hilbert space. Okay. In the next slide, we see the some process that works in quantum embedding. For example, the basis embedding, amplitude embedding, angle encoding, a feature map that I will see in the next slide. In this work, we use a feature map. The feature map is a function that map the classic data in a Hilbert space. For example, we have some points in a plane, and then we have to map these points or this data in a Hilbert space. So for this, we have to use this function. There is a kind of x. That kind of x is a input data, a set of input data, and we have to map this set of input data in a feature space that is a kind of f. And for this, we use a commonly feature circuit that is a CC feature map. Next slide, please. Yeah, CC feature map is one of the most used feature map in quantum machine learning. This feature map is a function. There is a classic linear function, and we use the C2C2 map use a phase gate, a classic phase gate. There is in matrix form in the slide, and a CNOT gate. So the next slide, please. Okay, this is an image from the Qiskit page that is a CC feature map circuit. So first we have Hadamard gates, and then we have unitary phase gates. Then we have a controlled X gate. Then in this circuit we have again unitary phase gate, then other controlled X gate, and this circuit could be repeated as we want. So let's go to see how to encode the data. Please, the next slide.
Sorry, I have a question.
Yeah.
Can you write the last slide? And can you help me to explain why we need the Hadamard gate at the beginning of each line?
Well, first we have to initialize the quantum state, and the Hadamard gate is a gate that, for example, we have one qubit, and this qubit is in the state 0. Let's with Hadamard gate we have to this qubit in the state 0 and the state 1. So in this case we have to 1.5 probability to the qubit is in the state 0 and the state 1 in the state 1. So in this case, this is a kind of initialize the quantum circuit.
Okay, thank you. I see.
Yeah, the Hadamard gate is a commonly gate in quantum computation. And in this gate, we have the option to change the probability of the qubit. For example, if we have one qubit in the state one, we have the 100% to of the probability that the qubit is in the state one. Instead of this, if we put a Hadamard gate, this probability is a 50% of that the qubit is in the state one or in the state zero. So that's the Hadamard gate works.
I see the working of Hadamard. So mm, I have another question related to the probabilities of the Hadamard gate. Mm, So why we need to the 50% for each test?
Okay.
Eh,
In this case, we have a Hilbert space. In Hilbert space, we have in the top side let me see, zero state, and in the both sides we have one state. So in this case, this Hadamard gate work as all the data not only in the top side. So we have to map all the data in all the block sphere, if you see as block sphere. So it's commonly used when you initialize a quantum circuit. In this case, this CC feature map is a quantum circuit. Is a small quantum circuit that this block Qiskit give us this block Qiskit. So this is how to the CC feature map is constructed. So if you, I don't know, for example, exist other quantum circuits in Qiskit as C, only one C feature map that use other configuration of gates, or a Pauli feature map that is a mix of CC feature map and C feature map, and have other another configuration of gates.
Thank you so much for the detailed explanation. Sorry for breaking you so much.
And don't worry, that it's very good. Yeah. Then we have a variational quantum circuit. Variational quantum circuit is how the data will be trained. In this case, we have theta. That theta is a parameter, and this parameter will be initialized, and then we have to send in a classic computer, and in this classic computer we have to optimize and evaluate the cost function, and as neural networks, this parameter is, I don't know, it's the equivalence of weights. So in this case, we have to optimize this parameter or these parameters, and then return this with a variational quantum circuit. So next slide, please. Okay, sorry for that, but this is in Spanish, but I will explain in English. Okay, the variational circuits variational quantum circuits as an circuits, quantum circuits. That first of all we have to prepare the initial state. This initial state is, for example, the data that is embedding in quantum. Then we have to apply a unitary quantum circuit. There is a set of parameters. In this case, the gates are a set of parameters. Then we have to measure these values or the qubits in order to see the output of this circuit. So in this slide we have the expected value of a circuit. There is there is a function of theta, and we have a bra with 0. Then we have a unitary gate with these parameters. Then we have the measure of the output. Then we have again the unitary gate, and then we have a ket of the state 0. So in this case we have a set of parameters that are theta, and this theta will be optimized with a kind of method. I don't know, the gradient method, Adam, Covilla, and this is the part of variational quantum circuits. Next, please. Okay, this is a circuit or a variational quantum circuit that first we have a rotation gates in the YX, and we have in this image we have 3 qubits. We have 4 parameters in the first line. Next, we have consolid X gates, and then we have other rotational gates, and in total we have 7 parameters. Next slide, please. Okay, then we have to obtain in the model. This is a mean squared error that first we have our target output minus our output. This is the formula of the mean squared error.
Okay, so as it was mentioned, for the optimization, we can use classical optimizers. So in this, for the to train the parameters of the ansatz. So the measures of the circuit, to approximate the labels, and in this case we use 3 different optimizers, which are Covilla, Adam, and SPSA. It was the last one. So I will explain a little bit about these optimizers. So the Covilla, the good thing about the Covilla is that it does not require to know it is not required to know the gradient function. So it's a good thing for some of the problems that do not have it. And well, it works by iteratively approaching the restricted optimization problems with linear programming problems. So when each iteration is done, well, the algorithm yields one possible solution, and afterwards it evaluates this solution using the objective and constraint functions, which yield new data in return to the optimization space. And well, it looks it takes this new data to see if the solution is more viable as from the last one, and each time that it cannot get any better, the step for each of the iterations gets reduced, and when one when the step is reduced to be as small as possible, the algorithm ends. And well, the good thing about Qiskit is that they have implemented this algorithm, so you can use the ones that are in the libraries. And well, some advantages over other methods are that you don't need to know the function's gradient, treats constraints individually when calculating a change in variables, and generally has a better convergence than other methods. Some of the applications for Covila outside of the ones mentioned here, it's planification, optimal search, resource allocation, and network optimization. Next slide, please. So here we have a little representation of what it would actually do. So as you can see, it is calculating the gradient using the parameters from the vector. And if a somewhat infeasible solution X is repaired with the help of the surrogate function of a constraint, the gradient is estimated. And if the close approximation to X is feasible, then you can change the step a step from X to Z can be calculated. Next slide, please. So another optimizer that is used is Adam. It is widely used in this type of operations as it is relatively new in the state of art. The good thing about Adam is that it adapts parameters according to the magnitudes mean of the weight gradients. This is similar to what another optimizer called RMS prop does. However, it differentiates itself from RMS prop due to the fact that aside from doing this, it also uses the second moments, which are the variance, the non-center variance, sorry. So Adam also uses the second moments. The good thing about Adam is that it adapts both the gradients for the average of the second moment, and it can be seen as an exponential moving average of the gradients and the squared gradients. It is a really good optimizer for noise applications, and you can see that it is easily manipulative. So for example, you have two parameters which are the decay rates for each of the moments, and one can easily manipulate these parameters. So having multiple tests is quite possible. Some advantages over other methods are that this optimizer is relatively new in the state of art, employs the characteristics of two other methods, AdaGrad and RMS prop, and its parameters can be easily manipulated. Next slide, please. So here we have some graphs showing how Adam works. The performance of Adam. So the green line shows how Adam performs without using the bias correction terms, and the red line is how Adam works using the bias correction terms, one of its many parameters. So you can see that with the green line, it works similar to another optimizer called RMS prop, and it is not a very good performance compared to when using a bias correction term. Here, what it is shown in this work, it's how the optimizer learns a variational automatic encoder. And as you can see, with values with values for beta 2 closer to 1, we have a better performance. However, we have to use the bias correction term. So this is why Adam is widely used, because it takes advantages of two other optimizers, and it performs better than any of those. Next slide, please. And the last one, which is SPSA. Well, the good thing about SPSA is that it's really cheap, computationally speaking. So one of the advantages is that you can use it with functions that have impossible to calculate gradients or are highly costly, or have a high cost. Sorry, or have a high cost. So it works by they use it to minimize the differential multivariate functions, and it does this by evaluating the cost function twice using the parameters of the stored vectors, which in this case it refers to when each of the element of the vector is displaced by a random generated value. The difference between SPSA and other finite difference methods is this one specifically, because for other difference methods, you need to displace each element, but only one at a time. So what you have to do is to iterate the over all your element. And when you try to do this in a very large sample, you get a really high cost for your computation, for the computation of the algorithm. So this is another advantage of SPS. It has a low computational cost. Also, it's really easy to implement, and it's suited for functions with gradient, which gradient is non-computational efficient or has a high cost. Also, as well as Adam, it adapts really good to noise problems. Can you please move to the next slide? Thanks. Here we have a graph showing how SPSA works. So these graphs were used to talk about a model predictive control problem, where we have, as you can see in the top bar, it's SPSA search path. So what they wanted to do here was to predict how some of these products, each of these lines in the below graph, the MSK plus 1, MSK plus 2, are products from a company. So they wanted to check how the demand for these products would be. The thing with this is that when predicting in the future, you need to be more careful, and it becomes complicated. So you cannot use a prediction model that stays constant. So using SPSA, you can adapt it. As you can see, the more we move into the future, which is the top graph showing how many days in the future we're predicting, SPSA is adapting really well to these predictions. Can you please move to the next slide?
Yes, but I think we just skip these few slides because it's extracted for the by the notebook. And after these slides, we're going to cover it. Okay. So far we discussed the workflow of the variational quantum algorithms. We're going to cover the implementation of this machine learning algorithm in a few minutes. We're going to run this medical classification algorithm. I think it's a good first approach to machine learning and quantum machine learning in Qiskit. And yeah, so I think as suggested future work, we could try to implement another quantum learning model, just learn just kernel or KNN. Yeah, we could try to use a larger data set, implement some kind of different matrix, because the one we implement is just the very simple, and try different quantum encoding scheme. So far, it's the end of these slides. We're going to take some questions before we move to the notebook. The notebook with Alberto and the foundation, but we noticed that some libraries are just how to say, are not compatible now. Like, we use quantum machine learning algorithms, libraries, and quantum Qiskit Aqua, but they no longer support So we just change it. This is the actual libraries we use, and we are going to share it again after this meeting. Well, for implementing this algorithm, we just start to import the libraries. The quantum machine learning libraries we are going to use are the feature maps and the optimizers that we just explained in the slides. Okay. The dataset we are going to use is a surveillance COVID-19 dataset from Indonesia, and it's just a base that identifies possible infection sources, about the patient in vigilance. We just change the codification of the dataset with 1 as a positive for some category and a 0 for indicate the absence of these symptoms. And these are the following symptoms and categories are in the dataset, and it's a two-class problem. We want to classify a patient in vigilance is under supervision or is monitoring. Okay, we define the class levels. It's two class problems, the PUS and the PIM. These are the class levels. We define a random state for validated. Okay, and a number of qubits based on the number of categories. And the next step is normalize the dataset. Anywhere where you have questions, you can ask it. Okay, so Saul, you want to explain this part, or I continue? The normalization of the dataset is really the same thing we just explained in the slides.
Yeah, you can continue.
Okay, so we are going to normalize the data on the surveillance dataset in a range of minus 2 pi to 2 pi. We split also the dataset because we are going to make some number of shots, and we just to make easier the handle of the data. We split it in a train set and a test set. These are just basic things in classical machine learning, and then we proceed to encode the data using the double C encoding map. Yeah, it's the same explanation we include in the slides, and we call a function the function CC Victor map. We applied it 2 times. Okay. We also include the variational form for the variational circuit. We combine these two circuits, and we also could draw it with these functions draw, and we obtain this image just to visualize the things we are doing. For these are functions to train the model, but we call it when we apply optimization algorithm. So I think I'm going to explain it when we get to that part. Okay. We implement 3 different optimization algorithms. In this part, we define it here just so the user could experiment or try the, the performance of the model with different algorithms and with different iterations. For example, we use the SPSA with just 45 shots, iterations, and we just get different results. Okay. In this part, we optimize the parameters. We call to train the model with this optimizer, sorry, and the function we call is to train the model. We use the objective function with initial parameters, and then in this function we are just to oh, train model optimizer cause yeah, cause function. Yeah, we're going to classify the the levels and the training samples. We just divide or categorize the samples with each class type or class category. In this class function, we just assign a parameters from a function. Um, we get the parameters of the circuit every time we call the model, and these parameters we get, we assign it to a state vector. The state vector is just a representation of the circuit or just a vector. Okay, could be a product or a polygates agent states. Well, we assign these parameters from a dictionary, and then we assign new parameters or values to our circuit, and we just evolve this state vector. The state vector contains the quantum circuit. We say evolve because we refer to a unitary. The unitary is where we store these parameters. When we get all for all the different samples of training samples, we just get a measure with this function. This function make a measurement and return a dictionary. The measurement is made in a computational basis. And we just call this return probabilities function that is defined here. This return probabilities function return a probability distribution over the model places. After measuring the quantum circuit multiple times, we get the probability of each label. And then we just count or store it in a variable. Sorry, because now we're going to use the minimum square error to find the difference between the correct label and the predict label. It's just a simple minimum square error metric. In this part, we can use different metrics to define the error or the accuracy. We just define the most simple. Okay. After we get these probabilities, we just update the new parameters and optimize it, and we print it as information. Then we can call the test model using these new parameters in order to differentiate is a correct level or it's a error. We just classify it. We use this couple of lines for every test sample. This part of classification it's also tunable. Someone can change it and get a better result. We just use the most simple we can implement it. Okay, and then we have the, oh sorry, this part is in Spanish, but it's the optimization parameters and the optimization value. And okay, it's fine. And it's a test accuracy. In order to change the iterations or the encoding, or implement some strategies to find the probability distribution, you will improve this accuracy. And this is it. This is the notebook. If anyone have questions, we can answer it at any